here we go. We are in the semiconductor materials. So I have a question. What comes to your mind when you say semi? I know the perfect semi is it is normally applied to a range of levels. It is of midway between two limits, right? If we have these two endpoints, so it is in midway. So that is semi, in the middle, right? So that is our topic for this day, the semiconductor materials. So to learn about the semiconductor, let us first know the types of the different materials. So we have three types. We have the conductor, we have the insulator, and we have the semiconductor. So they are categorized in terms of conductivity or resistivity. So first, what is conductor? Anyone? Okay. So conductor, here we are. Conductor is a material that will support a generous flow of charge when a voltage source of limited magnitude is applied across its terminal. So, a flow of current, this type of material will support a flow of current. So, pwede mo agi ang kuryente. Example of this are silver, copper, gold, and aluminum. So they are some prominent example of conductor. How about insulator? So insulator is a material that offers a very low level of conductivity under pressure from an applied voltage source. So meaning it cannot support flow of current. No current will flow, such as example of this, the prominent example of this are wood, glass, and Teflon. Right? So they are some prominent example of insulator. So example of that is also plastic. So plastic around the copper wire. So para di ka makurintihan, dapat natay insulator. Okay? So how about semiconductor? So semiconductor is a material that has a conductivity level somewhere between the extremes of insulator and conductor. So, naa siya sa middle part between sa conductor and insulator. Example of that, prominent example of that are silicon, germanium, and gallium arsenide. Okay, so these are the prominent example of a semiconductor materials. So the level of conductivity is also varied upon doping. So we will also learn about what is doping in the later session. Okay. Also, take note of the word conductivity. Conductivity is a measure of how well the material conducts electricity. The terms are, the unit of this are Siemens per meter. And the reverse of that is resistivity. And the measurement of resistivity is ohm meter. Okay? Inversely proportional to the conductivity of a material is its resistance to the flow of charge or current. That is, the higher the conductivity, The higher the conductivity, the lower the resistance level or the resistivity. So in tables here, in table 1.1, the resistivity rho in Greek letter rho is often used when comparing the resistance level of materials. In metric units, the resistivity of a material is measured in ohm centimeter or ohm meter. So the units ohm centimeter are derived from the substitution of the units for each quantity in this figure. So given that our area is 1 centimeter square, 1 centimeter square, and the length of 1 centimeter, then using the resistivity formula, resistivity is equal to R times area, resistance times area over the length. So we have ohm centimeter square over centimeter, then we'll cancel. So we have left centimeter, so we have ohm centimeter. So this fact will be helpful to remember as we compare resistivity levels in the discussions to follow. Notice in table 1.1 here, okay, notice the gap or the range of gap between the resistivity between the conductor and the insulator. As can be shown in the conductor, the resistivity of the copper as the conductor is times 10 to the power of negative 6 ohm centimeter, while the insulator has a 10 times 10 to the power of 12 ohm centimeter as mica, as an insulator. It can be observed that it has 18 places of decimal places as a gap. That is a huge difference between the conductor and insulator with respect to its resistivity. Also, notice and observe the semiconductor. It can be observed that they have an in-between values of decimal places with respect to conductor and insulator. The resistivity of germanium has 50 ohm centimeter, while the resistivity of the silicon has 50 times 10 to the power of 3 ohm centimeter. Germanium and silicon actually have received the attention they have for a number of reasons. One very important consideration is that they can be manufactured into a very high purity level. They have such a high, they can be manufactured in high purity level. In fact, recent advances have reduced the impurity levels and to pure material to 1 part in 10 billion. Imagine that. So you might ask if these low impurity levels are really necessary. So having a high purity level and low level of impurity, is it necessary? The answer is yes. Yes, they are necessary. Because if you consider the addition of 1 part impurity per million in a wafer, for example, we have a wafer and you have here an impure material added to this wafer, the silicon material can change from a relatively poor conductor to a good conductor of electricity. Imagine that. With that single impurity material, it can transform this whole silicon wafer from a poor conductor to a good conductor. So we are obviously dealing with a whole new spectrum of comparison levels when we deal with semiconductor mediums. So note also the ability to change the characteristic of the material significantly through this process is known as, okay, let me write, this is called doping. Okay, let me. Why is my handwriting so bad? Okay, I cannot write. So the act or the ability to change the characteristic of the material is called doping. So this process is another reason why germanium and silicon have received such wide attention. So further reasons include the fact that their characteristic can be altered significantly through the application of heat and light. An important consideration in development of heat and light sensitive devices. Also, we will be dealing this doping process in the next session. Okay. Some of the unique qualities of germanium and silicon noted earlier are due to their atomic structure. The atoms of both materials form a very definite pattern that is periodic in nature. One complete pattern is called crystal, and the periodic arrangement of the atoms are called lattice. Okay, so one complete pattern is called crystal, and the periodic arrangement of the atoms are called lattice. So for germanium and silicon, the crystal has a three-dimensional diamond structure. This is for germanium and silicon. The, okay, so any material composed solely repeating crystal structure of the same kind is called single crystal structure. For semiconductor materials of practical application in the electronics field, this single feature exists. And in addition, the periodicity of the structure does not change significantly with the addition of impurities in the doping process. So, dili ma-change ang iyahang periodicity kung mag-add ta og impurities on doping process. So let us now examine the structure of the atom itself and note how it might affect the electrical characteristic of the material. As you are aware, the atom is composed of three basic particles: the electron, the proton, and the neutron. So in the atomic lattice, the neutrons form the nucleus, while the electrons revolve around the nucleus in a fixed orbit is called while the electrons revolve around the nucleus in a fixed orbit. So I'll be showing you now the Bohr model of the two most commonly used semiconductor. So this is the Bohr atomic model of the most common semiconductor material, that's germanium and the silicon. So we have 32 orbiting electrons for the germanium. So this is for germanium. And we have, in the case of silicon, so we have 14 orbiting electrons. So in each case, there are 4 valence electrons. There are 4 valence electrons in the valence shell. So the valence shell is the outermost shell. So 1, 2, 3, 4. So we have 4 valence electrons for germanium, and for silicon we have 1, 2, 3, 4. So we also have 4 valence electrons for silicon. So in a pure germanium or silicon crystal, again, this has 4 valence electrons that are bonded to adjoin 4 atoms. Okay. So both germanium and silicon are referred to as tetravalent atoms because they each have 4 valence electrons to share. So let's go with the definition with the covalent bonding. The covalent bonding is A bonding of atoms strengthened by the shared of electrons. So, as you can see here, we have 4 valence electrons of silicon. Then a sharing of electrons side by side is called covalent bonding. Although covalent band will result in a stronger band between the valence electrons and their parent atom, it is still possible for the valence electron to absorb sufficient kinetic energy from natural causes to break the covalent band and assume the free state. Okay? The term free reveals that their motion is quite sensitive to applied electric field, such as established voltage sources or any difference in potential. These natural causes include effects such as light energy in the form of photons and thermal energy from surrounding medium. So at room temperature, actually there are approximately 1.5 times 10 to the power of 10 free carriers in a cubic centimeter of intrinsic silicon material. So what is intrinsic? Intrinsic. The intrinsic material are those semiconductors that have been carefully refined to reduce the impurities to a very low level. So, refined to reduce the impurities to a very low level, essentially as pure as can be made available through modern technology. So, an increase in temperature of semiconductor can result in a substantial increase in number of free electrons in the material. As the temperature rises from zero, an increasing number of valence electrons absorb sufficient thermal energy to break the covalent band and contribute to the number of free carriers as described earlier. This increase of number of carrier will increase the conductivity index and result in a lower resistance level. So therefore, semiconductors materials such as germanium and silicon that show a reduction in resistance and increase in temperature as increase of temperature are said to be negative temperature coefficient. Okay? So again, silicon and germanium are semiconductor materials that are said to be negative temperature coefficient because as the temperature rises, the resistance decreases. So you will probably, you'll probably recall that the resistance of most conductor will increase with temperature. So this is due to the fact that the numbers of carriers in a conductor will increase significantly with temperature, but their vibration pattern about relatively fixed location will make it increasingly difficult for electrons to pass through. So an increase in temperature therefore results in increased resistance level and therefore positive temperature coefficient. So earlier we have said that semiconductor materials such as silicon and germanium are said to be negative temperature coefficients. So while on the other hand, the conductor are said to be positive temperature coefficient because as the temperature rises, the resistance also increase. Therefore, increase. So this would be called as positive temperature coefficient. Okay? Actually, I have some experiences using this type of materials because actually I've been using this negative temperature coefficient as my current limiting device for my power management system. So it is very important and vital to uh, note these terminologies because you will know you will be using these materials in the future.